In this video, we are going to discuss what is the value of an excess pressure in a water drop against surface tension. Before I am going into the derivation, let me explain first of all to you that what is that excess pressure is, why there is an excess pressure inside a water drop. Let me explain that first, and then we'll go into the derivation expression for that excess pressure. Right? Let us consider a water drop. This is our water drop. You know, there is a property called surface tension that we are talking about, because of which the liquids always tries to acquire a minimum surface area. So that surface tension will always tries to pull the liquid inward, pull the liquid surface inward, so that the surface will be having a minimum surface area. So there is a force developed inside, right? For that force to be developed, we need to do some work. Surface tension need to do some work, right? So I can derive an equation for that work done by the surface tension, because of which it always tries to acquire a minimum surface area. So let me consider something like there is a total radius inside after say minimizing, let its radius is r, and the surface tension has reduced its radius by a value of dr. What I mean to say is, if you observe a little carefully, that its initial radius of that water drop is r plus dr, but finally dr is reduced and it has got a radius of r. So because of the surface tension, radius got reduced from r plus dr to r. Further, surface tension need to do some work. How much is that work done? Basing on the definition of surface tension, surface tension is defined as work done in changing the unit surface area of the liquid. That means work done is equal to surface tension into delta A. What is the area of this spherical body? Water drop is spherical, so area of that is 4 pi r square, because it is spherical. So its area final will be 4 pi. It has a radius of r plus dr initially, say, and then area that was shrunk down, right, is equal to 4 pi r square. So when I say change in area, I mean to say higher area minus lower area. Initially, it is having a higher area because its radius is higher, r plus dr, and it is shrunk down to r. So what's the change in the area means? 4 pi higher area, that is r plus dr whole square minus final area. It is reduced to a radius r, 4 pi r square. So how much is this? T, 4 pi I can take common, r plus dr whole square minus r square. Let me just expand this using a plus b whole square formula, that is a square plus b square plus 2ab, that you are very well aware. A is r, so a square is r square, b is dr. So value of that b square is dr square plus 2ab, 2r and dr minus r square. This r square and this r square can be cancelled, but the change in the radius that is happening is in micrometers, and the square of that even becomes 10 power minus 6 whole square becomes 10 power minus 12, and this value becomes too small. So as dr is small, dr square is too small, and that can be neglected. So if you neglect that dr square, I'm just scrolling the page up just for the writing further things. That implies work done due to the surface tension is T 4 pi. This r square and this r square got cancelled. This dr square we have ignored. How much is that? Is 2r dr. So that is one important expression that we have made. So let me tell you once again that what are we handling here, what are we trying to do here, what I have derived first. Let me try to explain that to you, right? So I said because of the surface tension, liquids always tend to acquire a minimum surface area. That means the drop who is having a area that I am showing pink as well as yellow. Inside it is yellow. It is initially having this much of the area, but because of the surface tension force, the drop has acquired a minimum surface area. The pink is gone. Let's assume it's having only a yellow area. So in reducing the total area from r plus dr radius spherical drop to spherical drop of radius r, surface tension must have done some work. How much is that? That is surface tension into change in area. So I have derived an equation for change in area, bigger area, that is 4 pi r plus dr whole square minus 4 pi r square. I have simplified and I have ignored dr square because dr itself is small and dr square is too small. So that I have got a derivation for the work done. See, if this much of the work is only working against the very shape of the water drop, that water drop could have crippled and gone, but it was not gone. It is there. That means what? There is some pressure that is developed inside the water drop, because of which water, the very existence of the water drop is there, right? To keep up that pressure, that water drop is also doing some work. How much is that work? We will try to derive an equation now, right? Let's try to calculate that value. Yes. How much is that? Let's try to calculate. Yes. Say, I'll just scroll down and derive. Due to excess pressure inside water drop, some work is done. How much is that work done is? Work done is equal to, say, force into displacement. The displacement that is caused in the diagram is only change in the radius, that is dr. This force, as I have to calculate pressure, I will define pressure as force acting per unit area, then force will become pressure into area and then dr. Pressure into area being a spherical one, finally having area of 4 pi r square, 4 pi r square dr. So this is the another amount of the work done due to that of the excess pressure. So this work done due to the excess pressure shall be compensated by the work done due to the surface tension. Then only the water drop is balanced, and finally it has got a shape that what it is supposed to have. So what I can do now, I can just equate this equation, work done due to the surface tension, to the work done due to the excess pressure. Just equate both of them, then I will get an equation for excess pressure. Let's do that, right? Equation number 1 with equation number 2, that implies equation number 1 says, yeah, this one, surface tension into 4 pi into 2r dr must be equal to excess pressure 4 pi r square dr. So this dr and this dr can be cancelled. This 4 pi and this 4 pi can be cancelled. This r and 1 r in this square can be cancelled, right? So what is remaining then? T is remaining, 1 2 is remaining. On the other side, T is remaining, radius is remaining, everything gets cancelled. That implies equation for the pressure or excess pressure, what I have derived itself is an excess pressure because this work is done by the excess pressure inside the drop. So people casually call it like pressure, but what we are actually deriving is an excess pressure by R. So that's the equation for the excess pressure in a water drop. So one thing that I want you to understand is surface tension of a liquid is constant and hence excess pressure is inversely proportional to radius. P is inversely proportional to radius. That means small drops will have a higher pressure and the bigger drops will have a lower pressure, lower excess pressure inside a water drop to protect themselves against the surface tension and to keep their identity on, right? So if you say, I just want to extend this discussion a little bit, What if we are talking about, say, if we are talking about soap bubble, not a water drop. How a water drop is different from a soap bubble? Water drop inside is filled with water. So it has only one free surface, that's outside surface. But if you draw a soap bubble, inside the soap bubble there is no soap. So inside is free, outside is also free. So it has two free surfaces. So in the place of writing the area, I would be writing not one area. That is while I am deriving the equation. This equation, I have written area. Yeah. Well, yes. While I am writing this change in area, I shall write not just one area, but I shall write another area, that is inside area and outside area. So what happens to the difference is, instead of the two that I have got here, as I have two free surfaces, two free areas, I will get another two. That is 2 and 2, that becomes 4. So what's the equation for the water drop? It's simply, that's for the soap bubble. For soap bubble, there are two free surfaces. There are two free surfaces. That implies Pxs is equal to not just 2t. For one surface, 2t. There is another surface, therefore there is another 2t. 4t by r. So excess pressure in a soap bubble is double to the excess pressure in a water drop, right? That's one point that we need to come. Right. As we came up to here, let us just extend the discussion a little bit further. Therefore, we can then conclude this topic itself. Right. Yeah. What is that is, if somebody asks you, what is the total pressure inside that water drop first of all, and then we can also talk about the soap bubble. So this is a water drop. Inside it is filled with water. So we found P excess, that is pressure excess, is 2T by R, having radius R. But this is an atmosphere. This atmosphere is also continuously applying a pressure on that. So if you want P total, we have to say pressure due to the surface tension and pressure due to the atmosphere P naught, that is 1 atmospheric pressure, or 1.01 into 10 power 5 Pascal. That much has to be added to find out the total pressure. If you are talking about a soap bubble, we won't be writing a 2T by R, but we'll be writing a 4T by R. That's how we can calculate the excess pressure as well as the total pressure in a soap bubble as well as a water drop. To remind you once again, the only thing that's different from a soap bubble to water drop is soap bubble is having an inner surface free as well as outer surface free. So there are two free surfaces based on whom the surface tension is acting. That's why it becomes 4T by R instead of 2T by R. Thank you for watching.